ECF22. We will start now with the presentation. I remember to the presenter to be strictly in the 15 minutes, and all the discussion will be at the end of the session. So I'll start with the first. It's entitled the Prediction Model for Fatigue Life and Limit of Steel Based on Small Crack Micromechanics. And please, presenter Hiroaki Ito. Okay.
Thank you, Mr. Chairman. I'm Hiroaki Ito from the University of Tokyo. Today, I will present you a prediction model for fatigue life and limit of steel based on small crack micromechanics. This is the outline of this presentation. First, I'll explain you the background and the objective of this study. Fatique fracture is the main reason for the accident of structures. And so it is important to predict the fatigue life and limit. It is known that these fatigue fracture properties are affected by microstructures. In spite of this knowledge and many researches, there are no quantitative models to explain the influence of microstructure. Fatigue fracture is divided into two stages. The first is crack initiation is called stage 1, and crack propagation is called stage 2. It is commonly known that fatigue crack behavior is highly affected by microstructures in stage 1 and stage 2, but these stages are not clearly defined, so behavioral microfracture should be captured. So this is the objective of this study. The objective is development of a general and quantitative model to predict fatigue properties based on microstructure information. In this study, we focus on ferrite pearlite steel because it is most widely used, and its structure is rather simple. So this can be the first and fundamental trial to develop a general model. Okay, so next, before a model is developed, stage 1 and stage 2 should be clearly defined. So in order to capture the early stage of crack initiation and propagation, fatigue tests and observation were conducted. So the condition of the test is shown here. In this experiment, tension and compression test is conducted, and the specimen is with a gentle notch in one side, so that the crack initiation side can be easily predicted. And this is the result obtained from the crack observation. As you can see, crack propagation seems to occur at the very early stage, and crack initiation can't be clearly distinguished. It indicates that crack propagation may be more important than crack initiation is. Sorry. And as you can see, there are more multiple slip systems in the last picture. So we focus on so we focused on the first grain boundary. So in this model, stage 1 and stage 2 are defined by the first grain boundary. And next is a model development. The outline of this model is here, and it is divided into 3 parts. And the first input part. As input data, material properties and the stress field is required. Material property is used for modeling of microstructures, and the stress field is used for stress distribution. Since the fatique fracture is said to be determined by strain, so the stress distribution is calculated from strain field in this model. To calculate the stress field, to obtain the strain field, in this model, finite element analysis is combined. In FEA, the effect of cyclic loading is considered. It is known that the stress and the strain relationship changes under the cyclic loading. So this equation is employed. So the effective stress distribution can be obtained by this equation. Next, modeling of microstructures. In this model, three-dimensional fracture phenomenon is assumed as a two-dimensional phenomenon. The surface plane and internal plane. Microstructures are modeled by randomly assigning grains in the surface plane and internal plane. And to simplify the assigning procedure, grains are assumed as ellipse with a specific area and aspect ratio and grain orientation. Geometric shape of ferrite grains are determined by grain aspect distribution ratio. So obtained from this grain aspect ratio and obtained from EBSD the ferrite grain diameter distribution. And the pearlite colony thickness, band thickness, is obtained from EBS optical micrograph as well. Next is okay, so I'll explain you the modeling of grain distribution in surface plane. In FEA, active zone and active surface and area elements are defined. Each grains are randomly defined in area element, and all grains are assumed as possible crack initiating site. So when the loading is over the resistance of grain, crack initiates. Okay, so let's move to the modeling of grain distribution in internal plane. And it is known that fatique crack propagates forming a semi-elliptical shape. And the crack shake aspect ratio changes as it propagates. And the aspect ratio is said to be affected by the stress distribution and initial crack shape. The relationship between the aspect ratio and stress distribution is shown in this equation. This is for long crack, but for short crack, initial crack shape is more important. So this equation is employed as well. So in this model, these two equations are smoothly combined, and this change of aspect ratio is considered. Since, as I mentioned, the fatique crack shape is semi-elliptical, and since it is complicated to model grain distribution in considering the change of the crack ratio, we focus on crack fronts. Crack fronts are assumed as straightened line with the same length as that of semi-elliptical lines. So the semi-elliptical lines are changed into straightened line. And this is the procedure of microstructure modeling. First, the grain is with specific area and aspect ratio and orientation is assigned in a line. And the grain is reshaped into a rectangle with the same area and aspect ratio. And the second, the grain is assigned in the same way and reshaped. And the grain diameters are averaged so that this equation is met. And so the next step, these steps are repeated until this equation is met. So this length is the same as this semi-elliptical crack front. And these steps are repeated until crack depth reaches the specimen thickness. The next, modeling of crack initiation and propagation. This model is based on a model called the interaction theory between the crack and the grain boundaries, also known as Tanaka-Mura model, proposed by Tanaka et al. This is the combination with Dugdale model and the continuously distributed dislocation theory. Slip band length and crack tip sliding displacement are calculated from these equations. And based on this model, the effect of a grain boundary can be considered. And crack growth rate is shown in this equation. This is called Paris law, and this is CTSE threshold, which means that crack arrestability. And in this model, driving force is effective shear stress. The effective shear stress is calculated using the effective stress tensor, and the effective stress tensor can be calculated from strain tensor, and also stress equivalent tensile remote stress is considered. I'll talk about it later. And material resistance is friction strength to move dislocation. This is a yield shear strength of single crystal. Because yielding is caused by the move of dislocation. This is employed as material resistance. And this is calculated by Hall-Betch law. And in this model, equivalent tensile stress is used. Since there's this stress distribution, the crack tip stress intensity factor is calculated from this calculator. And the equivalent stress is calculated from this equation. And to calculate stress intensity factor, weight function is employed. And the input sigma equivalent as driving force. Okay, so next, crack closure. Fatique life is said to be affected by crack closure, so the effect of crack closure is considered. For a long crack, the effect of a crack closure is constant, as shown in this equation. But for short crack, the opening stress changes, so this equation is employed to consider the change. Okay, so model integration. As I explained, stage 1 is propagates in first grain, and stage 2 propagates over grain lines. So in this model, these stages are combined. And threshold is shown like this. This is in stage 1, it's 0 because a single slip system is active. But in stage 2, threshold is this value because multiple slip systems are active. Let's move on to the model validation. In this model, these different steels are used. And compression test were conducted using smooth specimen. This is the same one as the that of observation, and full Wilson curves were obtained. And prediction of SM curves. Identification price law is parameters are fitted for only steel B. So this is fitted, and with this parameter, these predictions are obtained. And as you can see, it's a quite good agreement. So this is the conclusion. Faulty fracture is simplified as 2D phenomenon, and defects of microstructure can be obtained by this model. And the results are very good. Thank you.
Okay. Thank you for presentation.